Hi everyone. We will solve the second worksheet today. So we start with the second question. We will prove this equality, okay, when n is a positive integer. So we'll prove this by induction on n. So what's the base step? So for positive integers, n gets the first value that n can take is 1. That's why the base step is n equals to 1. Okay. So when n equals to 1, we have on the left, we have 1 times 1 factorial, which is equal to, again here, 1 plus 1 factorial minus 1, right? They both equal to 1. So we have the equality, right? When n equals to 1, we have this equality. So this statement holds for the base step. Now look at the inductive step. So for this step, we first suppose that the given statement is true for n, and we will show it's also true for n plus 1. Okay? Now let's write it for n plus 1. Okay? Write this equality for n plus 1, the left of the equality. Of course, we will obtain the right. Okay? So remember that if this statement is true for n plus 1, then we need to obtain that n times n factorial plus n plus 1 times n plus 1 factorial on the left equals to, this is factorial, equals to, here now we have, instead of n, we have n plus 1. So we have n plus 1 factorial minus 1, which is n plus 2 factorial minus 1. If this statement is true for all n, all positive integers, we need to show this for n plus 1 too. For n plus 1 too, it is correct. So we suppose it's correct for n and show it's also correct for n plus 1. So it means if it's correct for n plus 1, it means we need to have this equality. On the left, we need to have this, and on the right, we need to have that one. Okay, so we start with the left one. If you want to show some equality, you need to start from the left and obtain the right. Okay, or the opposite of that. You can start from the right and obtain the left. Okay, so for that, we suppose for n, it's true for n, and show it's true for n plus 1. So we start with the left one. We have this. As we suppose that it's true for n, so for this one, we know it's equal to n plus 1 factorial minus 1, right? As the statement says that, okay? So for n, we know it's correct. So till here, we have this. Plus, we have the rest here. So what do we have now? In the parenthesis of n plus 1 factorial, we get n plus 1 minus 1. Okay? So here we have n plus 2. Here we have n plus 2, n plus 1 factorial minus 1. And what does it mean? It means n plus 2 factorial minus 1, which we wanted to show, right? So this gives this equality at the end, says that this statement is true for n plus 1 too. Okay? Now we will find a closed formula for this one first. Okay, then we will prove our argument by induction. So let's try that for some values of n. So for n equals to 1, we have this 1 over 2. We just put n equals to 1 and get 1 over 2. For n equals to 2, we have, what do we have? Here we have 1 over 1 times 2 plus 1 over 2 times 3, right? When n equals to 2. So it gives us 2 over 3. For 3, we get this 3 over 4. For 4, for n equals to 4, we get 4 over 5. So you see, when we have 1, we had n over n plus 1, right? When we had n equals to 2, again we had n over n plus 1, right? When we had n equals to 2, we have 2 over 2 plus 1, which is 3. Okay, each time we get n over n plus 1. So what do we do? Now our argument is this, okay? We claim that this is equal to n over n plus 1, okay? This is our argument now. We will prove this by induction. So what's the base step? Remember, we started from 1, right? So for n equals to 1, this is base step. For n equals to 1, we had 1 over 2, right? We saw there n over n plus 1. So for inductive step, we have this. Now again, we suppose for n and show it for n plus 1. Okay, so here we have again the left side of the equality. So we suppose that for n, we know it is true. We want to show it is also true for n plus 1. That's why we write instead of n plus 1, okay? So for that, we need to show it is equal to n plus 1 over n plus 2. So till here, till this part, we know it is equal to n plus n over n plus 1, right? We assume that. So now the rest is this, so we add that here. Now we multiply this one by n plus 2. So we get n times n plus 2 plus 1 over n plus 1 times n plus 2. So what is this? This is n squared plus 2n plus 1, which is the square of this n plus 1, the square root of n plus 1. So here we have n plus 1 squared over n plus 1 times n plus 2. So if we isolate these ones, okay, we isolate by n plus 1. So we get n plus 1 over n plus 2, as we wanted to show, right? For n plus 1, right? For n plus 1, we showed that this is equal to n plus 1 over n plus 2. So we're done. We proved by induction that our argument is true for any n, okay, greater than 1. So for this, we need to prove that 3 to the n is less than n factorial. Now, this n will take values greater than 6, okay? So what's the base step? So what's the first value that n can take? It is 7, so this is the base step. Now, what do we have? We just compute 3 to the 7, which is this, and 7 factorial, which is this. So we have this inequality for n equals to 7, right? Now for inductive step, we again assume that the statement is true for n, and we will show it's also true for n plus 1. So what do we have? Here we have, so for n plus 1, we need to show that 3 to the n plus 1 is less than n plus 1 factorial, okay? At the end, we need to obtain this. So let's start with the left one, okay, left side of the inequality. So here we have 3 to the n plus 1, which can be written as in this form, 3 to the n times 3, which is less than n factorial times 3. Why? Because we assume that it's true for n. So we have this Okay, we assume this, and we will show it is also true for n plus 1. So we know this, okay, by assumption we know this. So 3 to the n is less than n factorial, so this is less than n factorial times 3, which is also less than n factorial times n plus 1. Why? We know that the minimum value that n can take is 7, right? So n is greater than 6, right? Because we will apply the induction on n when n is greater than 6. So it means if we add 1, n plus 1 is greater than 6 plus 1, which is 7, which is greater than obviously 3. So n plus 1 is greater than 3. That's why we can write n plus 1 instead of 3, and we will obtain something bigger than that, okay? Greater than that. So n factorial times n plus 1 we have now, which is n plus 1 factorial, right? It's equal to n plus 1 factorial. So at the end we have, remember we had before 3 to the n plus 1, which is less than this, and it's less than that, which is equal to this. So here we have inequalities, so we get this 3 to the n plus 1 less than n plus 1 factorial. Okay, so we proved by induction that this is true for any n which is greater than 6. Now we have a test which contains 10 questions, okay, and each question is has multiple choice. Okay, so we know that there are 4 possible answers for each question, okay. Now first we want to compute this. So for only one question, we know there are 4 many choices, okay. 4 many answers for one question, for only one question. So for each question, for the first question, he or she has 4 options, and for the second question, again he or she has 4 other answers, 4 many answers, right, to choose. So till this end, it will have 4 many other choices. So we have 4 times 4. How many times? 10, because we have 10 many questions. So we have 4 to the 10 many ways. Now for one question here in the part B, for one question we have, or the student has, 4 options, 4 answers, but also he or she can leave the answer blank. So actually the student has 5 many choices, okay, 4 answers and 1 option, which is leaving the answer blank. So now we will multiply 5. How many times? Again, 10 many, because we have 10 questions. So now we have 5 to the 10. Now for this is so easy. So from Boston to Detroit, we have 4 major routes, okay, as in here. And from Detroit to LA, we have 6 routes. So how many major auto routes are there? So here we have 4, here we have 6. So we multiply them and get the total, which is 24. Now we want to compute this, okay. We want the bit string to start with 1 and end with 1 again, okay. For the first and for the last digits, we know it has 1. Okay, how many digits are there between them? We have 8 many left, right? So for each one, we have 2 choices. For example, for this one, it can take 0 or 1. This one, it can take again 0 or 1. So for each one, we have 2 choices, and we have 8 many digits left. So we have 2 to the 8 many such bit strings. Now, to find the numbers which are divisible by 7, we have this formula. So between 0 and this says between 0 and 1,000, find such numbers. Okay, so first you will find the maximum number between them, which is divisible by 7. So after a few operations, you find this one, this number, which is divisible by 7, which is the greatest number between 0 and 1,000, and divisible by 7. And what's the minimum one? It's this is the least number, which is divisible by 7 in here. So you subtract them and divide them against 7, because you will find the values which are divisible by 7 between 2 numbers, x1 and x2. There should be at least 7 to both of them be divisible by 7. Okay, that's why you divide it by 7. And you add 1. Okay, so this gives the numbers, this means the numbers of this set, the number of this set, the elements of this set. So positive integers is divisible by 7. So this is the formula how to find the numbers, the number of the elements between 0 and 1,000, which are divisible by 7. Okay. So, but we want these numbers not to be divisible by 11. So what do? We need to subtract these ones, which are divisible by both 7 and 11. Again, we apply the same formula, so you find the maximum value in here, which is divisible by 77. Why we have this 77? Because if a number x is divisible by both 7 and 11, then it's divisible by 77, because they are prime numbers. Then this number, if it's divisible by these ones, then it should be divisible by this one. Okay, so you compute again this formula, and so you get this, which gives you the number of the elements here which are divisible by 7 and not by 11. Now we want them to be divisible by either 7 or 11. So here, as in before, here it gives the number of the elements which are divisible by 7, and this gives the number of the elements which are divisible by 11, and this gives the numbers, the integers, divisible by both 7 and 11. So we have this. Okay, because when we compute this and this, we compute 2 times of these numbers, which are divisible by both 7 and 11. That's why we subtract this one. Okay, it's the same to find the number of the union as in sets. Okay, how do we find the if A and B are sets? We find the the number of the elements of A union B as in here. Okay, so it's exactly the same with this. Now, which are divisible by neither 7 nor 11. So remember, we have this many numbers which are divisible by 7 or 11. And between 0 and 1000, we have 199 elements, right? Numbers. Or so if we subtract these ones, we get exactly what we need to compute. Again, remember the question, how many positive integers less than 1000 have distinct digits? So first note that we have this many positive integers between them, okay? So we will compute digit by digit. So the positive integers with 1 digit, we have 9 many from 1 to 9, right? And with 2 different digits, right? We want to find the ones with distinct digits. So the positive integers with 2 different digits. For this one, we can write the values from here. We can write the values from 1 to 9, right? So we have 9 many digits there, okay? Sorry, 9 many values here, okay? So what about this one? It can take, if this is 1, for example, if this digit takes the value 1, then we will start by this, right? But remember, we can write also 0 here. So again, we have 9 many elements here, 9 many values here. So here for this digit, we can write 9 number, okay, one of them. And here we can write 8 number, except this one, because we need to have different digits. But also we can write 0. So we have again 9 many elements here, so or choices. So we multiply them, 9 times 9. It gives us the number that we want to compute. What about the 3 different digits? Again, as in here we have 9, as in here we have 9, but here, for example, if we write 1, 2, here we can write 3, from 3 to 9, right? So we have 8 many choices in here. So we have this many number now for this part. So if we add them, we get this value. Okay, we get this value, which is we wanted to show, to find. Now we want to find the numbers between 0 and 1000, which have distinct digits and are even, okay? Now we have 2 cases to examine. If the last digit is 0, now what do we have now? So again, for this one, from 1 to 9, we have 9 many choices. And for this, as we want to have distinct digits, we have 8 many, because we cannot write here the number if we write it there, okay? So we have 8 many choices, other choices. So for that part, we have 9 times 8, okay? Because as in here, we have only one choice, which is 0, okay? So what about the others? As we want it to be even, so we have these options. So for the last digit, we have 4 many. What about this? As we write it right here, one of these ones, we have, instead of 9, we have 8 many choices. For this, we have 7 many choices, because as in here we wrote one of them, okay? But remember, we can write a 0 here. So we have again 7 plus 1, 8 many choices. So we have this many number, this many such number. Now what about this? We want to compute the number of the functions from this set to this. So remember, a function is defined by this. It takes a value from here, from this set x, and it sends it to y, but the image of this value, one value in here, should be unique, right? So each number can take only one element, only one image, can have only one image. So for 1, it can take 0 or 1, right? And for 2, it can take again 0 or 1, right? But only one of them, either 0 or 1. So for each one, for each value in here, there are too many options, right? So it is 2 to the n, because we have n many number there. We have 2 to the n many different functions. Now we want to find the functions, such functions again, but now we want it to be one-to-one. So we have some cases. If n equals to 1, then we have either this function, if this set contains only 1, okay, it can take 1 as the image or 0. So we have too many functions. If we have n equals to 2, then we have a function from 0, 1 to 0, 1, okay? Actually, from 1, 2 to 0, 1, sorry. So 1 can take 0 or 1, and 2 can take 1 or 0. So again, we have too many functions. We cannot write a function like this. Which take 1 and send it 1, and which take 2 and send it 1 again, because we want it to be one-to-one, okay? That's why this is not an option, and neither with the zeros, okay? This is not an option either. So we have only 2 functions, which are one-to-one from the set 1, 2 to 0, 1, okay? Because we set n equals to 2. What about this case? If n is greater than 2, then we cannot write a function which is one-to-one, right? Because if, for example, if n is 3, we have here this set, we want to write a function from this set to this. So let's say f1 equals to 0 and f of 2 equals to 1. But what about f of 3? We had 0 and 1 before, and we want it to be one-to-one. So, but there is no other element in here to be the image of f of 3, okay? So there is no function, no such function if n is greater than 2, okay? Now we want to find such function which assign 0 to both 1 and n, okay? We want the image of 1 and n to be 0, okay, as in here. And for the rest, they can take 0 or 1. So for each one in this set, there are 2 options, to be 0 or 1 as the image. So, but how many numbers in there are there? There are n minus, here we computed, n minus 1, minus 2, plus 1. So the last value, n minus 1, minus 2, the beginning value, plus 1. This is a formula. So n minus 2 many elements in here. And for each one, there are 2 options. So 2 to the n minus 2 many functions there are. Now we want, again, compute the number of such functions which assign 1 to exactly one of the positive integers less than n. So for some fixed x, okay, we know that f of x equals to 1. And for the rest, for the values in here except x, we want them to have image as 0 because only x takes the value 1. Okay, so there is nothing to compute. There is only one such function. Okay. Now we have 6 people, which includes the bride and the groom. Okay. So if the bride must be next to the groom, how many arrangements are there? Okay. We want to compute that. So first, see that bride and groom as one person. Then how many people are there? So we had 6 before. The left one is 4 then. And with this bride and groom, we have 5 many people. If we think bride and groom as one person. So we have 5 factorial. So this gives the arrangement of these 5 many people. Okay? So, but remember that bride and groom can rearrange inside them, okay, between them, sorry. So, for example, they can change like this, okay. So we need to count that too. So it is 2 factorial because in here we have 2 people, okay. So this gives the number of the arrangements, all arrangements, where the bride and the groom are next to each other. Now the bride is not next to the groom, so all arrangements are 6 factorial, right? Because we have 6 people, all arrangements are 6 factorial. The arrangements where the bride and the groom are next to each other is this, as we did that in here in part A. So if we subtract them, we will obtain this one that we desired. So this gives the number of such arrangements. And the bride is positioned somewhere to the left of the groom. Now we want them to be like this, okay? Bride and groom, not groom and bride, okay? So we have 5 factorial because we see them as one person, okay? So we have 4 left, so 4 plus 1, we have 5 factorial. Now you need to read the definition. A palindrome is a string whose reversal is identical to the string. What does it say? Actually, for example, 1, 0, 0, 1. So here we have 1, 0, 0, 1, and it's reverse again. 1, 0, 0, 1. It's reverse again. The same with the previous one. So it says it. What about this? So its reverse is 0, 1, 0, 1. So this is not a palindrome, but this is, okay? So let's compute this. How many bit strings of length 6 are palindromes? So if we have a palindrome, we need to have read from this from right the same string, okay? So if we have 1, 0, for example, 1, 0, 1, then here again we need to have, sorry, here we need to have 1 because of this, and 0 because of this, and 1, Okay, now let's read from the right. We have 1 0 1 1 0 1, which is exactly the same with this, right? 1 0 1 1 0 1. Okay, so it's enough to compute only the first 3 digits. Okay, so for each digit we know there are too many options. It can take 0 or 1. Again, it can take 0 or 1, and this will take 0 or 1. So we have 2 to the 3 many strings, such strings. Okay. What about this one? If the length is 7, now we know the first 3 ones will determine the last 3 ones, and this can take any of the values, right? 0 or 1. This will not change anything. So we have now 4 many digits to choose. So we have 2 to the 4 many palindromes of length 7. Okay, because each one can again take 0 or 1. So now we have 2 to the 4. So now we want to compute the again the number of the palindromes, but now the length is n. We have 2 cases. So if n is even, as in there, here we had even length. Okay, if n is even, then how did we compute that? We had 2 to the 6 over 2, right? So we have 2 to the n over 2 many palindromes. What about if n is odd? If it's odd, here remember we had 2 to the n minus 1 over 2 plus 1, right? Let's compute there. If this is correct, then we need to have, if we put n equals to 7, we need to have 2 to the 4. So 2 to the 7 minus 1 over 2 plus 1. It is 2 to the 6 over 2, which is 3, plus 1. So we have 2 to the 4, right? Exactly the same number. So if it's odd, we need to compute it by this many palindromes there are. So that's it. See you next week.